So we've talked about alkene structure and geometry, but now we're going to talk about alkene stability, which is going to have a big impact on reaction outcome. Remember, the more downhill reaction tends to happen, we're going to make what is most stable. To know what that is, we have to think about stability of different molecules. So right here we have a bunch of different molecules, and the bullet point says that alkene stability increases as the number of R groups increases. And what we're really talking about is the number of R groups that are attached to the alkene itself. So as far as the alkene, that's the carbons that are involved with that double bond. So that carbon and that carbon, this carbon and this carbon, this carbon and this carbon, et cetera, et cetera. So these carbons are the ones that we're talking about the number of R groups increasing. So this would be an unsubstituted alkene. This would be a monosubstituted alkene. Mono is a prefix meaning one. This would be a disubstituted alkene. This would be a disubstituted alkene too, because there are two carbons coming off of this same side of the alkene. This is also a disubstituted. So all three of these are technically disubstituted alkenes. And while I have them in a specific order here, they are all generally pretty similar as far as their stability. We talked previously about how trans is more stable than cis. That's true, but they all have the same number of R groups, so they're in the same ballpark is what we'd say. This one is a tri-substituted alkene. It's got three carbons coming off the alkene, 1, 2, 3. And this we call a tetra-substituted alkene. So the more R groups there are, the more stable it is. So stability of the molecule increases this direction. This is most stable. This is least stable. So what is the phenomenon behind that? And it can kind of go along the same lines as what we learned about carbocations. So we talked about carbocation stability. The more substituted the carbocation, the more stable the carbocation. And we rationalize that because delocalization of charge is stabilizing. It's stabilizing. So a secondary carbocation was more stable than a tertiary carbocation. Sorry, a secondary carbocation, what I meant to say, walk back that last comment, not true. What I meant to say is a secondary carbocation is more stable than a primary carbocation. And we rationalize that through this idea of hyperconjugation. And I have a figure in your notes for that. Essentially, the CH bonds are electron donating, and they can line up in the same plane as the empty p orbital of a carbocation and donate some of their electron density to that p orbital. And it turns out that the same thing is the case for pi bonds. If we had a CC pi bond and we have these p orbitals, essentially when we have a CH that lines up with those orbitals, even though it's technically a full orbital, all delocalization is pretty much a good thing. There's one case that we'll talk about in organic chemistry too where delocalization can be not a good thing, but in every other case, delocalization stabilizes organic molecules. And essentially the electrons in this bond are delocalized into that pi bond, into those p orbitals, and that makes them more stable. So the more groups we have around that pi bond, the more stable the molecule becomes. If you imagine with the tetra-substituted example on the top right, we're going to have 4 different methyl groups that could do that delocalization, and that stabilizes the alkene to a great extent. So, how does this impact the reactions that we're going to learn about? Good question. We're going to hit that right about now. All right, so how does this greater alkene stability impact our organic reactions? And this brings us to this rule that a Russian chemist named Zaitsev discovered just empirically. He was running reactions, and they noted that in eliminations, the more substituted alkene forms in the greatest quantity. At that point, they really had no idea why that would be. Why is the more substituted alkene forming in a greater quantity? Now we have access to a lot of higher level experiments where we've essentially learned that it's because of this hyperconjugation idea. It's because of the greater delocalization that stabilizes molecules. But at that time, really, they were only able to observe, oh, the one that's more substituted forms to a higher degree. And because of that, it was pretty revolutionary at the time, so it's their rule, Zaitsev's rule. So what does that mean about this reaction right here? We have an alkyl iodide, it's tertiary, and what happens in this reaction, right? We have a base, and remember, what is it called? It's called beta elimination. So where are the beta positions? This is the alpha position. This would be a beta position. This would be a beta position. And this would be a beta position. So essentially, that's the thing. We have problems here because there are multiple beta positions. There are hydrogens in that beta position, hydrogens in that beta position, and hydrogens in that beta position. So what happens in an elimination reaction is the beta hydrogens get pulled off. Those electrons form a new pi bond. But it's going to be a different product if we take that beta hydrogen versus that beta hydrogen. So which one is going to form? And this goes back to what I said a long time ago. In organic chemistry, negatives flow to positives and the ball rolls downhill. Ball rolls downhill, that's my second rule of organic chemistry. You only need 2 rules. What the ball rolls downhill means is we form the more stable product. Which one of these is the more stable product? Answer that before you move on in this video. Hopefully it's very clear. The more substituted one is. The tri-substituted one is more stable than the di-substituted. This is tri-substituted. This is di-substituted. So this is the more substituted alkene. The base is going to, in a greater quantity, grab that hydrogen or that hydrogen. Either of them are going to make the same molecule. Electrons would go down there, kick out the iodide to produce this as the major product. And there will be some of this formed as well, but it'll be a minor product. So that's Zaitsev's rule. That's why it matters that we have an understanding of alkene geometry so that we can predict the correct product. All right, we'll do more of this soon.